Hello everyone, my name is Takieddine from the University of Technology Belfort-Montbe in Belfort, France, and I'm gonna present to you our paper entitled Curiosity-Driven Learning for the Visual Control of Non-Holonomic Mobile Robots. The outline of this presentation is gonna be as follows. First of all, I start by introducing the context and motivations of our work. Then we're gonna delve into the proposed approach. Next, I'll present the experimental setup, and finally, the results and conclusion to this presentation. In this paper, we explore solving the problem of visual servoing of non-holonomic mobile robots using deep reinforcement learning. Classically, this problem is approached using image-based visual servoing, which aims at regulating the robot at a desired pose in its environment, given a desired image sampled at this pose and images captured at instant t. This is done often by minimizing the error between the visual features extracted from the desired and current images, and then this error is used to compute the control law to drive the robot to the desired pose. However, this problem is quite difficult, mainly due to the non-holonomic constraint, which makes it challenging to perform certain maneuvers. Also because the world is 3D, whereas the employed images are 2D, and also because losing correspondence between the desired image and current image results in visual servoing failure. So we want to learn a goal conditioned stochastic policy function that maps current and desired images to control velocities. And our research question is, how can we leverage deep reinforcement learning to address the visual servoing of non-holonomic mobile robots? The related work to this paper is the paper entitled Learning View and Target Invariant Visual Servoing for Navigation, presented in ICRA 2020. So before we delve into our approach, we need to frame this problem as a reinforcement learning problem. Learning VS can be formulated as a partially observable Markov decision process in which we need to define four entities: the space, which we define it as the pose of the robot; the action space, which is the control velocities, angular and linear, executed at each instant t by the robot; the observation space, where at each instant t the robot receives an observation, that is, the current and desired images; and as for the reward function, we define our reward function as the Euclidean distance between the current pose and the desired pose. To approximate this stochastic policy we combine two ideas in deep reinforcement learning: a policy model where we use recurrent policies for policy learning, and an intrinsic curiosity model where we use intrinsic motivation to enhance the exploration capabilities of the robot. So in our proposed DRL approach, the policy model, we consider it to be a recurrent policy trained with PPO algorithm. Initially, we apply visual domain randomization on input images to enable zero-shot transfer to the real world. Then the randomized images are passed through a CNN encoder to generate features, which are then passed through an LSTM layer to tackle the issue of partial observability. And finally, the policy outputs control velocities and an estimate for the value function. For the intrinsic curiosity model, the key idea is to reward the robot for maximizing the statistical distance between the observations distributions induced by the current and the old policies, and this can be done by approximating Rényi divergence between these two distributions. I'm not gonna delve into the mathematics of this method due to the short time, but the key idea is that intrinsic rewards and the Rényi divergence can be approximated as a function of intra and inter-episodic distances between the features in these observations distributions. And since these intrinsic rewards are approximated in feature space, we're gonna use an encoder that is an inverse dynamics model, in our case trained to predict actions given to consecutive observations. And the reason we use this encoder is that it allows to overcome the variability induced by the visual domain randomizations on observations. For the experimental setup now, for training to enable zero-shot transfer to the real robot, we design our training scene to closely resemble our real scene, and during training, the initial pose of the robot is randomly sampled. For evaluation, we consider a test set of pre-sampled 100 initial poses, and for the metrics, we consider distance error and orientation error averaged across this test set. And for the compared methods, we compare our approach to classic image-based visual servoing and learning-based visual servoing, as well as various ablated versions of our methods, such as training without intrinsic rewards and comparing to other intrinsic curiosity methods, as well as comparing the encoder used for observations. Now for the obtained results, the table of the left shows the obtained errors. Clearly our method outperforms the classic image-based visual servoing and the existing learning-based visual servoing. And we can see also further the improvement that brings the intrinsic curiosity methods, and this can be also seen clearly on the figure 4 on the right, where the trajectories performed by the robot under our method are clearly superior. And now for the results, we can see here two videos of simulated experiment and its corresponding real-world transfer. Our method is capable of driving the robot to reach a desired pose. So now for the conclusion, in this paper we tackle the problem of visual serving of non-holonomic mobile robots. We present an approach that combines recurrent policies and intrinsic motivation, and we show that our approach outperforms classic image-based visual serving and the existing deep reinforcement learning method. Thank you for your attention. For further questions, please contact me at this address email.